we will start with the live demo. In this case, we are going to show you how to design the control loop for the three-phase two-level power factor correction rectifier. In this case, the three-phase rectifiers plays a crucial role in various applications, like, for example, electric vehicles, chargers, grid energy storage, etc. However, the interaction between the EMI filter and the three-phase rectifier often leads to system instability. So this is a very important thing, because if you do not contemplate the EMI filter in the control structure, in the processing that you are designing the control loops, maybe your control will be unstable when you put the EMI filter. So I'm going to show you some examples later. So SmartCtrl address this challenge by providing the frequency response of the key transfer function in the three-phase two-level rectifier. SmartCtrl comprehensive analysis ensures and thorough understanding the stable solution. So the first step, we will open the SmartCtrl software. Then I show you how to design step by step the control loop for the three-phase two-level PFC. And then we want to export the control loops to third-party simulation. In that case, we are using PSIM and SIMBA. So let's start with the live demo. In this case, I will open SmartCtrl. Okay. As mentioned before, this is the initial dialog. In that case, we are going to the three-phase PFC boost converter option. Click on. Let me move the SmartCtrl window here. Okay, this is the first window that appeared in that case, the single light diagram. Here, you can configure different types of, for example, in the three-phase, the typical three-phase control structure, we have the DQ control. And also, we have different options. For example, if you want to design the control loops in the alpha beta domain. In that case, in the alpha beta, we have two types of compensator. One is the PI, and also we have the proportional resonant compensator for the inner loop. Here we have also, we can tune the control structure in the digital control, for example. For the modulator case, we have a different type of modulation. In this topology, we have 5, the typical PWM, the space vector, discontinuous one, and discontinuous maximum and minimum. Also, we can define different types of loads. For example, it's a simple resistor, a constant power load, or for example, if you have a constant current. If you select the option of DQ control, you need to define one of the PLL, the phase looked loop. In this case, we have two different types of phase looked loop. For example, the synchronous reference frame and the quadrature soggy synchronous reference PLL. Also, we can define a different type of EMI filter. We have 4 predefined topology, the most typical structure of the EMI filter. And also, for the main filter, that is this inductance, we have you can tune the compensator for the simple L filter or LCL filter, and also if you want to apply some active damping, or maybe you can use a passive damping. So as a first step, I want to tune the compensator for the DQ control. The modulator, I will select the space vector. And in the first example, I don't have the EMI filter. So then I have to close this window. And here in this toolbar, you can see the different options that you have to define the input data. So if you go to the power stage window, here you can define the parameters of the power stage of the PFC. So in this case, we have the grid voltage, the line frequency, etc., the power, and also the switching frequency, etc. After that, we have to click on OK and close this window. In this option, in this button, we can tune the phase looked loop PI. This is the synchronous reference PLL. And here we have a PI and VCO in order to estimate the phase of the grid. So in that case, we have also to open, we have to go to this icon. This is the body plot for the transfer function. And here, if you can see, we have the plan of the PLL. This is the open loop transfer function for the PLL, and also we have the closed loop in the brown trace. And in this case, also we have, if you go to this icon, this is the solution maps for the PLL. So we have different way to select, to define the crossover frequency. For example, the first option is to define the crossover frequency manually. You can here put, for example, 30 degrees, and also we can select some of the crossover frequency and click on OK, and also the body plots are updated automatically. So another option, for example, you can define the stabilization time or the damping rating. Manually, again, if you can change, you can define these two parameters, and also you can modify directly the proportional constant of the PI or the time constant of the PI. So in that case, I select the crossover frequency and the phase margin. And also, you can move the cursor on the solution maps, and you can select one point of this of the white region. Also, in the phase looked loop window, you can define different type of alienation. For example, if you want to make that one of the grid voltage, for example, if you want to do the ED equal to 0, or if you want to do the EQ equal to 0. This is for alienation. So in that case, I will select align to ED. That means that the EQ will be 0. So this is here, you can see that we try to do that the component Q of the grid voltage will be equal to 0. If I change to the EQ, the PL structure change a little bit, and also you can see that in that case the due component of the grid voltage will be equal to 0. So in that case, I select the ED, click on OK, for example. Now I close this window. The next step is to define the current sensor. This is the current sensor window. Here we can define some of the gain of the current transducer. Also, we can define some bandwidth of the current transducer and some offset. And we have also, you can, if you have different options, for example, for signal conditioning, if you want to adapt the gains in order to that the current sensed current will be in the range of the span of the ADC, for example. Typical value is like 0 volts to 3.3 volts, or for example, 0 volts to 5 volts. Also, you can have you have to define some signal conditioning. Also, you can select the option for a second order low pass filter. For example, this represents an anti-aliasing filter, for example. And the last step is the unity feedback. So the unity feedback is the inverse gain, in order that compensate all the gains that you set before, in order that your magnitude, that you will control will be in real value. So that means that if, for example, if we have 100 amperes in a real converter, so the sensed in this point, the sensed current will be equal to 100 amperes. So in that case, I select just the unity feedback gain, and here I want to select, for example, 100 milli as a gain. So click on OK. The next step is to define the grid voltage sensor. So in this case, also we have just a gain. Click on OK. I set 1. And also we have similar windows in order to define the input parameter for the output voltage sensor. So in this case, again, you can select the option of signal conditioning, the low pass filter, and also the unity feedback gain. So in this case, I select the gain, for example, 30 milli, and select the option, the unity gain feedback. So in that case, I click on OK and close. Now we have a window for the modulator. Here you can define the amplitude, the peak value of the carrier signal for the triangular in this case. So in that case, I set equal to 10. Click on OK. And now it's time to tune the inner current loop. So for this case, it's important. This is as mentioned before, this is the transfer function for the plots. So here I will activate the transfer function, for example, the current plan. This is the current plan. This is the pink trace. It represents the open loop transfer function of the current plan. And also you can see here in the brown trace, the closed loop of the current plan. So again, we have another solution maps if you go to this icon, and here, this is another solution map. In that case, is for the current loop. So remember that solution map represents the relationship between the crossover frequency and phase margin. So in that case, you can move again the cursor for the solution maps in order to see the response of the transfer function. So in that case, also you can move, you can set by manually the phase margin and crossover frequency, and also you can define directly the KP and the time constant for the PI compensator. And also you can, we have two types of implementation of the PI. This is the standard form, and also you can select the parallel form. So in that case, you can define the KP and the integral constant, KA. So I select the standard form, and here I select one phase margin equal to 50 degrees, and also the crossover frequency equals to 7 kilohertz. So, as you can see, this point is stable, will be stable. And after that, you have to tune the output voltage compensator. In that case, you have to go to this icon. This is the output voltage compensator. It's similar to the current. In that case, also, you can define the phase margin, crossover frequency, and also we have another solution maps here. This is for the output voltage. So I want to disable this transfer function, and I'm going to enable the voltage plan. This is the output voltage plan. This is the open loop for the output voltage transfer function, and also this is the closed loop. So again, we can move the crossover frequency and first margin, etc. So in that case, it's important that if you move the crossover frequency of the inner loops, the region of the output voltage solution maps change, because the inner loops is faster or have more bandwidth than the outer loops. So in this case, I set that this is equal to 7 kilohertz and 50 degrees. And in this case, I set that crossover frequency equal to 1 kilohertz and here 50 degrees. Okay. So this maybe I want to show you here. Okay, the control loops will be stable. So in that case, if you go to this icon, this is the schematics. It's like a summary that you can see here, all the combination that you select. We have the power stage. We have, this is the control structure for the DQ control. We have the coupling current axis. This is the two inner loops. This is the part transforms, and we have this here we have the modulating signal, and also we have one PI for the output voltage. This is the sensor current, and also we have the configuration of the sensor stage. This is the modulator, and also this is the PLL. So after that, it's time to export the results. In that case, okay, in that case, I'm going to this icon, click on here, and we have two options. So the first, I want to export directly to PSIM. In that case, I select the schematics. For example, I set a name, sample 1 PSIM. Click on OK, and you have two options. You can use the element PSIM functional elements. This is the version I want to show you. Click on OK, and now you can see that SmartCtrl create a PSIM template for you. Here we have the power stage, we have the sensor stage with the transfer functions. Also, we have the control structure that I showed you before, and this is the modulator. And here we have the PLL. So in that case, I want to increase a little bit the total time. And now it's time to run the simulation. So here in the parameter file, you can see all the parameters that you define in the SmartCtrl. And also you can see here the constant for the PI compensators. So this simulation is finished. Okay. Here you can see that this is the output voltage, achieve the output voltage reference. And also you can see, for example, the currents. This is the three-phase current. And also you can see, for example, the modulating signal. This is the modulating signal. Remember that it's not saturated because the carrier is, the peak value of the carrier is around 10, from -10 to 10. And the modulated signal are inside this range. So also you can see, for example, the theta that is estimated by the PLL. So in this case, the system is stable. Okay, now I want to export the same result to SIMBA. So in that case, I select this option to SIMBA. Now it's time to set a name again. For example, sample number 1, SIMBA in this case, and then I want to click on open. Now SmartCtrl is creating the SIMBA schematics, and now SIMBA will be open. Here, SIMBA will be open, and again, in that case, let me put a limiter here, in order to limit the current. So I put one here, and then I want to select the limit of the current. In that case, from minus 100 amperes to 100 amperes. Okay, and then click on Run Simulation. Again, we have here the power stage. This is the transfer function of the sensor stage for the current, the output voltage. We have the modulator. This is the PLL in that case, and this is the control structure. We have the output voltage control loop and the two inner loops, and also we have the current decoupling. So if we go to the results, you can see here the output voltage. The output voltage achieved the reference. Also, you can see here the three-phase current. Here we have the three-phase current and the modulating signal again. So as you can see, the control loops is stable. So I want to close this and close this option. So now, as mentioned before, we have our control loops is stable, and I want to make just one modification. I'm going to the single light diagram. In this option, I want to select one of the EMI filter. For example, I select the structure number 2. If you go to the EMI filter window in this icon, click on OK. This is the structure of the EMI filter. In that case, we have one stage for the differential mode here, and one stage for the common mode here. And also we have a damping network, passive damping network in this field. So here you can modify all the parameters manually. And also, if you go to this icon, represents these windows, these body plots represents the attenuation for the differential mode and common mode. This is a very useful tool. For example, if you set you change the parameter of the EMI filter. For example, I set here 1.7 and click on OK. Here you can see you can check if the attenuation that you want a specific frequency is achieved or not. So this is very useful in order to design a preliminary filter, an EMI filter. So after that, just in the power state, the only modification that I set is the EMI field. All the rest of the all input parameter, I won't change. So in that case, as you can see here, our control loops is still stable, but it's important in that case to analyze the Middlebrook criterion of, for example, the phase margin and gain margin and phase margin stability criterion. So that means that we have to analyze the output impedance of the EMI filter and the input impedance of the PFC. So the input impedance of the three-phase is a very complicated transfer function. So SmartCtrl, if you click on, for example, in the input impedance here, you can see this is the transfer function of the input impedance, the frequency response. I want to disable the open loops. And also you can see here the output impedance of the EMI field. So in that case, it's important that verify at the intersection of the both impedance, what is the phase margin. So the phase margin, the different phase between the both impedance will be less than 180 degrees. So that means, for example, if I select this point, here you can see that the output impedance phase is around 86 degrees, and the input impedance of the the input impedance of the phase of the input impedance is around minus 124 degrees. So if you make the difference, you have to more than 180 degrees. So that means that our control loops will be not stable. So if I again export the simulation to PSIM, so in that case, I said another name, sample2 PSIM, click on open and select the S-domain coefficient. So now we have this is the power stage, and also we have the EMI filter here. And we have some parasitics capacitance that are connected to Earth in order to emulate the common mode current. So now I want to change a little bit the value of the total time, and I want to increase a little bit the limit of the PI compensator of the inner loop, for example. So increase here. Okay. Now I click on run the simulation, and we have to wait a little bit. And in this case, we'll see that the control loops is unstable. As you can see, the output voltage is oscillating, and also if you go to the inductance currents, you can see that it's not okay. So, and also you can see the modulating signal. It's not stable, the control loops. So in SIMBA, we can get a similar result. And in that case, okay, set the name sample number 2, SIMBA. Click on open. Now SmartCtrl is creating the schematics. Okay, again, in that case, I have to put the limiter element in the currents to 100 amperes minus 100 amperes. Okay. In that case, I clicked on OK. Now it's running. So here we have the EMI filter starter as a sub-circuit. If you double click on this gray box, you can see here this is the same EMI filter configuration that we have in PSIM. We have the one stage for the common mode and one stage for the differential mode. So if you click on results, also here you can see the output voltage. As you can see, the output voltage is unstable, and also the currents will be unstable. So similar results. Okay, click on OK. So as you can see, the main important to analyze the input impedance and output impedance of the EMI filter and the three-phase PFC rectifier. So one of the solutions, for example, if I decrease the crossover frequency of the output voltage loop, for example, to 500 Hertz. In that case, the control loops will be stable, and if you check the phase difference of the both impedance, for example, In that case, you can see now that the input impedance of the three-phase PFC, now it's around to minus 60 degrees. And the output impedance of the EMI filter, it's around to 83 degrees. If you make the difference, it's less than 180 degrees. So in that case, the control loops will be stable. Now we want to check the simulation to PSIM. Okay, again, I set another name, sample number 3, PSIM. Click on OK, and now S domain. This is the schematic simulation. As mentioned before, I modify the limit of the PI compensator of the both currents. And I want to increase a little bit the total time simulation. Now click on OK. Now I have to click on and run simulation. So in this case, the control loops will be stable because we comply with the impedance criterion. So this is the simulation results. We have the output voltage achieve the reference. And also you can see here, this is the inductance current. Now this is stable. And also you can see the grid current that is already filtered by the EMI filter. And also you can see the modulation side. As you can see, all is stable. So now we can get a similar result in the SIMBA. Go to SIMBA, sample number 3. Okay, SIMBA. Click on open. Now SmartCtrl is creating the schematic simulation. So we have the schematic simulation. Again, we have I have to put the limiter. Here's, and now is click on OK. Go to results and also to the output voltage. And now you can see that the control loops is stable. So again, we can see the currents and the modulating segment. So the design is now stable. So okay, this is how to design, for example, the control loop for the three-phase two-level power PFC rectifier for the control structure is implemented in DQ control. And also we have another option. For example, if you go to PSIM simulation, go to schematics. If you, for example, I can set another name, number 4, click on open. You have the option that is called C code. If you click on this option, in that case, all the control structure, as you can see, is implemented in the DLL block. If you double click, you have to use an external file, a simulation file, and here you can see the sample control number 4. Click on OK. So SmartCtrl create the C file for you. And here you have, this is the typical, for example, this is an initial code in order to implement, for example, in a DSP or a FPGA, for example. you have the equation editor of the PI, the difference equation of the PI compensator. Here you can see we are implementing the phase looked loop, the control structure, and the modulator. All is in the C file. So here the sine and cosine function are implemented as a lookup table. That it's a very useful form to implement the trigonometric function. And also you can simulate this option. Okay, SIMBA, I said okay. And here I have to decrease a little bit the time step. Have to click on run simulation. The simulation takes some minutes. And here you can see how the control loops is implemented if in the C blocks. So we have the output voltage, and also we can see the currents. For example, these currents. Okay, the simulation takes some minutes. And that's it. Okay. Maybe I want to close this. No. Another important things in the 3-phase 2 level, as mentioned before, is that you can also, for example, tune the compensator for the LCL filter. In that case, if you select the LCL filter, one of the important things is that the main restriction of these types of converter, of types of filter, is the LCL is a third order filter, and we have a resonant peak here. So this resonant peak limit our bandwidth of the control loops. So in that case, SmartCtrl, you can see, for example, you have two different options. You can select the active damping, for example. If you select the active damping, in that case, the control structure modify a little bit. We are sensing the current through the capacitor, and also you have a gain that is injected as a perturbation in the control structure. So that means, for example, if that gains, I can change this value in the power stage windows as this is the name KD. And for example, if I increase this value, the resonant peaks is more attenuated. In case, click on OK, and now you can see the resonant peaks attenuated. And this is very useful form in order to increase the bandwidth of your power converter for the case of the LCL filter. Another typical wave is, for example, the passive damping. In that case, we have a resistor with capacitor that are in parallel with the capacitor of the main filter. So this is another way in order to attenuate the resonant peak. In that case, in the power state, also you can here change the value. For example, the resistance, click on, and you can see how the resonant peak is increase or decrease. So this is a very useful option in order to, for example, to design the control loops for the LCL filter. So that's it. If you have